Welcome to today's webinar. The topic today is generation of wind loads based on CFD in RWIND 2. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, German and English webinars, etc. I will be the moderator today and I will answer your questions together with Markus Baumgärtel. But my two colleagues can introduce themselves. Andreas, it's your turn.
Hello, I'm Andreas Niemeyer from Dlubal Software. I'm responsible for the development in cooperation with Mr. Dlubal, and mainly I take care about our wind and farm finding products.
Hello, my name is Markus Baumgärtel. I am responsible for customer support and FAQ, and today I will answer your questions during the webinar.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. You can ask questions via the control panel on the right side of your screen. You can enter a short question here and we will answer you. If you don't get an answer during the webinar because there are too many, you will get an email after the webinar. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Then with the content, I hand over the screen to Andreas Niemeyer. Just a moment. Okay, Andreas, let's go.
Thank you, Andreas. Okay, then I overtake. So we prepared today a webinar for you about RWIND and RFEM6, our new program generation, and to show you how you can work with these tools in our program. We selected here 4 main points to explain you how this is working together. So generally I want to explain you today how you can specify wind load parameters and wind load cases in RFEM6. Then how you can move these RFEM models into the numerical wind tunnel and can start the calculation, and how you get back results from this, let's say, CFD calculation in RFEM and can do further statistical and design calculations. And finally, I want to sum up all this stuff, let's say, with calculation methods from, let's say, our wind, numerical wind tunnel, where we offered in the last years only a steady flow calculation, and now we also offer since a few weeks a transient calculation, how this is working, how you can start this, and how you can investigate the resulting results from this calculation method. So, and this brings me now to the point that we can jump into the live demo, maybe as only for imagination. You see in this slide 2 pictures on the right side. What is maybe our model, what we work on today. So you see here a U-shaped roof, a canopy roof, and this is maybe this model where we show everything today. So you have an imagination what is it about. So let's jump in, going to RFEM6 and load a model. Generally I like to show you directly how we can set up such a model, but I have only 1 hour for this webinar, so we have to start with a prepared model. So this is my canopy roof here, and I scheduled that we open it in this way, that you see it in this style with, let's say, rendered cross sections, with many supports, with dimensions, and maybe to start with a question, is it needed or not, or what all these supports are doing? And for questions, if it's unclear if this symbol is needed or not, in RFEM6 we offered many tooltips, or we implemented a lot of tooltips. So only draw your mouse pointer over such elements what are unclear, and you will get a hint what is about. So you see here it's a effective length setting. So it's a visualization for the buckling length input for the design. And this brings me to the point to show what is this model about and what we predefined. So we predefined even here, or RFEM 6 did it already. We had here already design settings for columns, pin support members, for longitudinal members, and for the, let's say, wing members. And you can do a full design if you calculate all. If you don't need these symbols, you deactivate it. So deactivate it and you get what is the point. Our model, you see we have here a circular hollow section as cantilever column, a box section with a big torsional stiffness, and here tapered eye sections with a cap member, eye section also, and with some filling members. What about C sections? And this is our model, what we want to design today. If we take a look on our load case list, you see what our author of this model already did. So we see we have here a self-weight load case, and if we calculate this self-weight load case, we calculate all, we get, let's say, the load case results plus a steel design, what means we get here our bending moments from self-weight load case. So you see here bending moments, normal axis forces, but also a steel design. And here you see if I calculate this model only with steel design, for this self-weight load case we get a utilization about 7%. Not much, but it's clear we don't set up more loads. What is the case of our webinar today? So if we go back now to our load case list, we see we have to fill it to get the right design, to get the right utilization for all actions what could appear for this roof. And we can fill it now with maybe wind load cases. So if you generally have to design the structure, you create here wind load cases based on a standard. For this type of model, we know our standard offers us for canopy roofs load schemes, what you can apply. This is maybe quite exhausting because you have to calculate resulting forces for every wing and to set it up. And today I want to show you how you can solve this with a CFD-based analysis. For this, you have to prepare our program in a special way. You have to specify the tasks. This task you can specify generally in the base data. So if we go here on the top entry and open base data, you will see in this tab add-ons all tasks what are possible. So here is specified steel design, what I just showed you, and a wind simulation add-on, what means we can do CFD analysis. So all tasks are defined and the program mutates according to these settings and shows you everything what is needed for doing this. So let's close this window and open a wind analysis setting. So for this we open a new load case. So when we want to do wind analysis, of course we can give a load case name. For example, wind in. So the question is where, in which direction we want to design it. So let's take a look. We see, okay, maybe Y direction could be interesting for this structure. So let's write in Y. Okay, then as next topic we get here a lot of options, and you see we have here analysis type. Static analysis. This is maybe for pure structural calculation. But if you open this box, you will see there is a new item wind simulation. And this wind simulation is connected to this add-on wind simulation in the base data, what we just checked in the as task. No? And if you activate wind simulation, you will get here two further tabs for detailed sub-settings, and you get here some options to specify static analysis setting, action category. Action category, of course, could be wind in our case, imperfection, structure modification, inertial state. So you get here a lot of options, and the question could arise, is this really needed for a CFD calculation? Why I have to specify here if I want to calculate according second order or large deformation? I agree, it's let's say in the first point of view questionable, but you have to know that wind simulation is a two-stage calculation process. What means? If you calculate the load case with the type wind simulation, the program is moving your model into the numerical wind tunnel, doing a CFD calculation, extracting from the wind flow around the model pressures on the model, moving these pressures back to RFEM and doing a statical calculation, a structural calculation for these forces. So one point CFD calculation, second structural calculation. Therefore, you have to specify here also static analysis setting, imperfections, and so on. Then let's take a look what is hidden here below these two tabs. Wind simulation. So of course you get here a setting what is about the CFD calculation itself. Take a look inside. Here you see, do we want to make a steady flow or transient flow analysis? So we can say clear, maybe we call this setting steady flow. You see you have here a list, you can define more than one setting. You can give every load case a separate setting if it's needed. Then you can specify here maybe the density, kinematic viscosity of the medium. You can say if the turbulence should be considered, if the boundary condition of the bottom boundary of the wind tunnel should have a slip boundary, if you want to consider roughness, if you want to have a user-defined dimension setting for the wind tunnel, what was a wish in the past from some users, the mesh sizes. Then you have more sub-settings about the steady flow itself, how many iterations, about the turbulence model, about the accuracy, how big the residual pressure should be, and some advanced settings. So here you specify all calculation parameters for the CFD calculation and can give, let's say, the setting a name. Then we specified how the calculation should be done, but the question is, with what the calculation should be done. We know CFD calculation is something like a numerical wind tunnel, and we have to give the program the feedback what he should send into the wind tunnel. Of course wind, but with which speed. And here you get an option to set a wind profile as boundary condition for the wind tunnel. And if we check this data, you will see you have here two options. You can, let's say, pragmatically define this wind speed and turbulence diagram by giving table values manually, or you can create this wind speed diagram based on a standard input. So we know all countries have some standards for describing the wind loads on specific sites. There are existing wind zones or whatever, and according to this data you can create such wind speed diagrams. We coupled this, let's say, information of the standards with a map. So you can also click the place on the map. So maybe let's create our or simulate our model in the garden of our boss. So let's search the place of our company here and zoom in, and let's say okay, we place this model here, and overtakes the site-specific data with geo-coordinates, with address, with altitude. So you can say if the turbulence should be constant or not, and so on. So you specify the input for the wind tunnel. And with confirming this window, you have overtaken it into this setting. Then the program needs, let's say, finally one last information. We wrote it here in the text. The wind should run into or flow into y direction. It's clear, it's only a stupid text here, but you have to define here the direction of the wind. So it's a clockwise direction about C, and this means 0 degree is in X, so 90 degree is in Y-axis. Now the program knows everything to do such a calculation. Well, means he knows the calculation properties, he knows the wind speed, he knows the inclination, and here in the last tab he only informs us about the size of the wind tunnel because we selected a model depending automatically defined wind tunnel size detection, let's say. And so here it's only information about the sizes of the wind tunnel. And if we confirm this window, the program will update the load combinatorics and draws us the wind tunnel in the graphics. You see wind tunnel, input wind speed, and here is our structure. So far everything looks nice, and we can press the button calculate, of course. But I don't want to do this because we want to speak about wind simulations in our programs, and I want to show you what is behind. So let's do this two-step calculation of wind simulations I mentioned manually. In this case, I open the locus 2 again and open the sheet wind simulation, and you see here a hidden button, and this button shows us what will be transferred into the numerical wind tunnel. Let's open this. And you see here we have, let's say, our wind tunnel with terra, with model, entrance, with all properties, so steady flow, flow parameters, all calculation parameters, all this stuff is defined here, and yeah, we can start calculation. So I do this, start calculation. This is maybe what is behind. So if you press calculate in RFEM, the program will move this model like this here in the wind tunnel and will press the button calculate. And then the process is running down all these steps, what means he creates a shrink wrapping mesh around this sharp-edged model from RFEM. This is maybe we call this a simplification step, and we do this to make it wind-proof. What means if you see such things here, this coming from this rough modeling of a structural model, but we don't want that the wind should go inside, so we make it windproof, we bind a foil around. And with this simplified model, what we create from this sharp edge model, we can create a mesh between this simplification and the wind channel sides around the model, and can calculate the flow around the structure according to defined calculation parameters. Here, a steady flow. You see the process is already running. It's an iterative process, and it's ending until he reaches the predefined residual pressure. And after he reached this, he will calculate maybe the pressures on this shrink wrapping mesh around the model to the real structure and prepare us forces for the further structural calculation. So now he finished. You see he just starting the transformation or extrapolation process to the original model, preparing graphics, and now he asked me a question, should I change to RFEM back? Of course, we can do this, but we want to take a look inside what happens. So now, and let's take a look on this shrink wrapping mesh, what I mentioned. So this is the model simplification. Yeah, the program makes it windproof by binding a foil around and calculating the wind flow around, let's say, around this model, and creating from this wind flow around pressures, or it's a result of this flow around, and creates from these pressures a pressure skin on this model. And these results will be used in RFEM for calculating the structure itself with the wind loads. But what you see now, and this was my target. Yeah, if we take a look on this member structure, of course we see he binds this foil around, but we see also the wind flow is running through the model. Yeah, you see it can go through the roof, and this is not real. So of course structural engineers create these structures without doing a cover on these structures, but in wind calculations you need a cover that the program knows here is a cover, the wind cannot run through the roof. So and this is the point what I want to show, that if you work with structural calculation models in wind tunnels, you always will suffer this problem that the wind can run through your model even with all tools what the programs are offer. The interfaces will only transport the data what you send in and not more. So you have to prepare your model for this type of calculations, and here we placed some really powerful features in our new generation to solve this task. So therefore I cancel this calculation, I close the window. This we can close, and go back to RFEM and check how we can solve it. And for this task we invented a new type of surface. So I changed to wireframe model, and we say here select boundary and select here the type stiffness type, load transfer surface. And you see this is a surface type what have no stiffness, so it will not brace your structure. It only takes loads and transfer it to the members what belongs to the surface. What is exactly our topic. So let's select these boundaries and place the surface inside. Of course the program will delete the results, but this is quite regular here. So now when we turn on rendering, you see we have this surface inside, and we can go ahead with our wind calculation. But at the moment I said this surface has this property, but I don't show you how this is working. So let's take some minutes to explain how this surface itself is working and which features you have. So the first feature of a surface in member structures is that you have here a coordinate system of the surface itself, and this gives us the option to orientate members according to this. So if we check maybe the input, you will see, oh, the author of the file don't place these members right, but we can select it now and can say right click, properties of members, edit, and go to the rotation, and you see we have here rotation types, angle, and let's say help node, what let's say almost all programs have. But we have also now orientate according surface, according this surface. And this is a really powerful feature because now the members orientates according this surface. The same is maybe for the another wing side. So select all three stripes, members, edit, and go here to section, surface, and pick this surface. And without calculating any angles, you can place the members on the right place. Then let's take a look on the power of the surfaces itself. For this, we move this load case 2 to 3 and make here a gap. And we say, okay, we place here, for example, a snow load. And give here action category snow. Oops. Okay. Now let's define some snow load to show how this surface is acting. Now here we say snow loads are always projected, so projected in Z direction with maybe a unit load of 1 kilonewton per square meter on both surfaces. And you see the program automatically distributes the surface load to line loads, but on all members, so not only on these members what are overtaking the loads in reality, then on all members what are existing. And here we have some properties of the surface. So you see here you can control the view in the navigator. You see this is our basic load and it will be distributed like this. And if you want that the load is only distributed to specific members, for example, we want to distribute it in Y direction, we go here to properties, surface, edit, and say here load transfer, and transfer it only in Y direction, and say also maybe the surface have a weight of 1 kilogram per square meter. And you see the view is changed. Now the program changes the snow load to only to these, let's say, filling members, and the filling members transport the load to the wing members. And even for, let's say, surf weight, you see this 1 kilogram is distributed over the surface. So the load transfer surface can act integral over all load cases. So not only for surf weight and snow, then also for wind. And this is maybe the target. So you can create now wind models which having these surfaces inside. So if you check, you see now we have a surface inside and it looks quite good for our simulation. We have a compromise between wind model and structural model. But if we take a closer look, we will see, the wind tunnel only see everything. So he cannot differ between surface and members. The question is, what is now the point? Generally, the wind will maybe act on the surface and then the surface gives the loads further to the members. How can we give the wind tunnels this information? And here our team also invented a new feature, or let's say it prepared it. I close this application again. I don't want to save. And jump in, and for this we have to open the mesh settings. You see in the mesh settings we have here a further tab, wind simulation. This tab rules everything what is transferred to the wind tunnel. It checks maybe the size of mesh, of this shrink wrapping mesh. It rules maybe the mesh near the cross section, if the sections are meshed correctly or maybe quite rough. And here we have a function if maybe which elements will be moved to the wind tunnel. In this case is checked all active elements. So this means if we say please move only this column, and this column and these two surfaces, if we make this only visible, then and start the wind process, then only this model will be analyzed. And this is exactly what we want in this case. So if I start maybe here now the calculation, run analysis, maybe now from RFEM that you see the difference. here you see maybe two calculation processes. This is a two-stage calculation. At first he's doing the CFD calculation, and in the second part the static calculation. Always what you select you will see in this information windows. Of course, because we changed the elements with the surface and members, you have to do the shrink wrapping meshing again, and also the CFD flow again. And after he gets this, he does the static calculation. And maybe to make it more comfortable to you, we transfer even the in-time calculation information, something like this convergence diagram, what is a pure information from the RWIND program. We transfer it through our programs that you see also the reaction of the calculation directly in our program, or thought it's two independent programs. And this helps always to understand, oh, do I work with the right model, or is there a convergence issue? I have to stop calculation, whatever. Yeah, so everything is possible here. Generally, what is important to know, if you're doing calculations with RWIND, it's possible to cancel these calculations and the intermediate results remains. So this is especially interesting for calculations which takes longer time. So you don't have to wait maybe until the final residue is given. You can stop it before. But now we define such a rough mesh to have a short calculation time that we get directly results. And you see here the program ends up with a, let's say here, deflection of everything with forces in the members. So this is the static structure calculation. But let's make a short check if he worked with the right model. Open maybe the internal information, and you see, okay, the program calculated here the structure only with the surfaces and the members, and you see we have here our suction on the top, our pressure on the bottom, and the netto pressure will overtaken to RFEM, and the wind flow is now not through the roof then, on the side, on the upper and lower side. So now when we're using these results in RFEM, you see that we get these forces here. And what is interesting, or what I want to show, is if you go here to maybe a visibility only to the C members, you see these members will get maybe the force from the wind loads. You see here our shear force diagram. You see it working like a continuous beam because I defined here scissor hinges. And finally, they will give their loads to these wing beams as shear force diagram with a further bending moment. And in the next instance, the columns, or maybe over the box section, the column will get the bending force from the final wind load. Yeah. So all this is one integral process, and with this wind load case we can update our load combinations. So when we go here to our load combinations, the combinatorics will update the load combinations, and if we calculate all, we can calculate even a result, a design result from these new wind loads. So this is the mighty of RFEM 6, that even the design is running in background without any action from us as users. I get finally here, besides static analysis, even still design, where you see the program draws us on all members, maybe let's use wireframe model without load display, a utilization diagram over everything. And if we go here to result by member, you see our biggest result is now here almost by 50% by considering this wind load case and snow load case what we just defined. So, and now we coming to a point that we say, okay, we can sum up the calculation and do the rest. But if we talk about canopies, we always talk also about how much wind can flow below the roof. Sometimes there is maybe a shading or whatever. And I also got in past some questions about, can we simulate shadings in RFEM and how we can do this? And we talked also as team about how we can solve this. And we know RFEM could be used as modeling machine quite good in this case, and we go into this direction. So if we have, for example, here a shading inside, we can use RFEM for it. So let's copy these 2 points here and go into a new model, shading 1, and model a shading, how it looks like. These 2 points, I only have that I know how big the shading should be. And let's draw a plane view of this shading. So maybe if I compare it with a railway station, you always have here such a shading with such cavities where the people can sit. So and we simulated it's 2 meters high, so maybe -2 meters, and copy this step with surfaces and go, and we have here something like this, such a shading box. And this shading we want to simulate in our wind model. For this we create from this model here an IFC file, what is really new in RFEM. So we can create IFC files. Of course, the program warns me because the surfaces have no thickness, but this is no important here because we only producing wind models. We store this shading on maybe desktop, SH1, store, and now we can go back to still construction model and insert it. So we import here an IFC, SH1, and overtake it. And you see we have the shading now inside. And it's not a surface, then it's a IFC model without stiffness. We get it here in a specific BIM navigator where we can also deactivate and activate some surfaces, but this model could be used for our wind. And as mentioned before, we have mesh settings where we can rule which elements will be moved into the wind tunnel. So if we go here to the mesh settings and say wind simulation, surrounding model, all IFC objects, and OK, and check our wind input, like before, what will be moved into the wind tunnel, then you will see we also have here these shading elements now inside, specified as separate model. Oops. Here my RFEM model, here my shading element. So this is possible, but this brings me also to the question, what is with my terra? So we have here shading elements, but you can ask me also, can I simulate the terra? Yes, of course. And is this needed in, should I define this in our wind or in RFEM? And we took care that you can rule terras now also in RFEM. Let's take a look on how this is working. Because terra is quite a global setting, we placed it here in the base data. You see, you have here a tab for terra where you can say, I have a horizontal plane. We can set it here. We can move it. We can say maybe move it 2 meters down. Or we can say, let's take an inclined plane by giving or defining a coordinate system which we rotate maybe 5 degrees around X. So all this is possible. We can specify shading elements, terras, in RFEM. So, and if you say, I have a more complex terrain, not only a plane and the inclined plane, it's also possible. For example, let's model a terrain. And as mentioned before, you can use RFEM as modeling machine for it. So let's open a new model, TR1, for example, and specify a grid of nodes, maybe I know for 15 by 15 meters quadrant segments. So let's copy this node here 3 times in X with 5 meters. You can also use 1 meter, but it's up to you. It's only a input. And here with minus 5 meters. Let's take all, copy this row in 5 meter in Y direction, and now finalize it here with copy with minus direction here. And now we have all nodes in this scheme here. And now we can model a terrain with these nodes. So for this, I take a top view and select all nodes. Moment, this is, yeah, fine. We select all nodes, deselect maybe this top level, and move the other nodes, for example here, 2 meters down. And if we check this, you see this is maybe our level. On the top our roof is standing, and then the program should create the terrain in this node set. For this, we select all nodes in the table nodes, Ctrl C, go back to our model, and go back to base data, terrain, and say here, table. Here we have this basic terrain dimensions, how big it is, and here we have a table, and we Ctrl U, and we get all properties in, and you see we can also model other terrains, and you can organize it in RFEM. And if you say now in the mesh settings, wind simulations, terrain, no IFC objects, only from model, then the interface knows when it transfers data to the wind tunnel, even the terrain should be considered. What helps? Because now we have the tools to make batch processes for different wind directions. What brings me to the next point. Therefore, we fight it to have all this data in RFEM, that we can only move this data to our wind. So let's find a solution for this last task. So I just mentioned, now what happens if we have the shading and we want to simulate different wind directions now? Should I define all these wind load cases manually in this load case list with different angles? Of course you can do this, but this is boring work. For this, I recommend let's delete this load case and go to the wizards. So maybe here, go to wizard, go to wind simulations, and here we have a machine which creates for you, for a specific calculation settings, what we already defined for a wind diagram, more load cases. We can say we have a step angle of 15 degree and it should start from 0 to 90 degree. And with this wizard we get these load cases for every 15 degree segment automatically. No big deal, I would say. If we confirm this setting, we have all these load cases here. They are blocked and are based on this without setting. Now we can start calculation. I don't want to wait with you for this solution, therefore I prepared this data in an already calculated file. So open this model here, steel construction with 15-degree segments, and take a look. So here is our result with the Terra. You see we have here static analysis settings with forces already, and if we take a look here on these load cases, you see if we take a top view how the wind tunnel is running around the model. Yeah, quite impressive, I would say. And for every load case we get this CFD forces for further design. And if we, let's say, go now into a calculation all step or calculate steel design, then the program updates the design. Of course, it, let's say, if you check load combinations, you see the program is checking maybe with snow as leading, then with wind as main force, and with wind as leading. All situations will be combined together and results finally in a steel design result by nearly 83%, where you get from our tool not only a figure, then you get the result for every member separately, the result. And if you are interested maybe which leads to the biggest result, you see CO21 is governing here, and here maybe this check gives you this utilization. So this to this main connection, which ends up in the case that you see how you can specify wind situations, how you can create wind load cases in RFEM 6, how you can move data into the wind tunnel and get results back for further structural calculation. And I have now 1 point left, what is about calculation options of the wind tunnel itself. And as mentioned before in the introduction, we have now let's say we worked since the introduction of RWIND with a steady flow simulation type, what gives us the average time solution. We extended it now with the pro level of RWIND, that you can also calculate the transient flow analysis. Here in the interface for RFEM, you can change the setting or create a new one, and all, let's say, wind load cases will update it with this calculation setting. Of course, no big deal. But the question is now how this is looking like in RWIND itself and what we get as difference. Before you saw when we checked our wind results, you get always for one time step or for this average time step one solution as time average. And now we calculate also results over time. And this is looking like this. For this I open our RWIND model. And you see this is our model with shading, with Terra. We have here some values, but they are not interesting right now. So let's deactivate it here. And now, as mentioned, as different to this steady flow calculation. So here in the setting, you get here maybe if I start a transient flow, of course this setting is changed. So transient flow means now that we can calculate not only one solution, what is average, then we detect in the beginning, before the calculation, according to model properties, a simulation time. So we found an algorithm to find out the suitable simulation time. So here the program recommends to calculate 11 seconds period for this model with time steps of 0.11 seconds. And this results finally in many time results, and here you see even the change of this transient solution. For steady flow you got one result, what is the average, and now you get for every time step an individual result. For the transfer of data to RFEM, this is, let's call it status quo. At the moment I can only transfer one time step, what is declared as master time layer. What I can specify here, what is the master time layer. But in our RWIND you get all results here with these different time steps until the 11 seconds. So if I change here, you will see the colors will change in the graphics. So let's go here to another, and you see values and colors are changing. Of course I can change here even in this bar, or I animate it. You will see how this wind flow over the time of 11 seconds will change the pressure skin on the structure, what have of course effects on the structure calculation also. So this is one effect. Of course you can visualize it also with other results around the model. So here in this case you see maybe the magnitude of wind speed, and if you animate this stuff you will see how the magnitude is changing around the model, what have finally then effects on the pressure on the model. But for me, of course, these are colorful pictures, and if you are the designer of such structures you need more than such colored pictures. So even if you visualize maybe these vectors of wind flow where you see how where these, let's say, turbulences, or not directly turbulences, and the wind directions are changing, you can visualize it here over time for this 0 to 11 seconds. Of course, this is maybe a lot of data what we have here for this model and for this space around, but if you are interested in, let's say, in detailed results, what I absolutely understand, if you have to decide if it's good or not good and so on, you got more tools in the program RWIND, and you will see these more tools in this navigator. You see we have here in the navigator now zones, materials, point probes, line probes, point clouds. All these tools helps you to investigate the data. And let's start from top to bottom. So what you can do with zones. You see I predefined here already 3 zones, and maybe you saw also here a zone display mode, and you see my cursor selects now elements or model or terra and writes directly which zone, and you see this is zone 2, zone 1, zone 1 is wing 1, in this dark blue, this green is wing 2, and 3 is columns. What I have here predefined. All others is zone 0. Of course we can create here new zones, so this could be a list what is longer and assign these elements to it. But what is the goal of it? And the goal of it is that after you defined these zones, you can visualize only this one zone or the other zone. You can do this with results. So if you maybe say show me the pressures on the model, you see maybe only the pressures on the zone 1, zone 2, or both. You can do this for the surface result or also for drag forces. So you see here the drag force only of this zone, drag force of the other zone. So even this is possible. And not only to sum up everything to one drag force, then even if you go back to the navigator, you see if you go to zone, you go here to edit and see in the info box the size of the zone, the drag force of the selected time step. Here quite interesting, average pressures over the zone for the full surface, for the top side, for the bottom side, the same for CP coefficient. So all this data is here summed up per zone, what is interesting for interpretation of your model. Then, of course, the zones have a second task also. So, and this is connected to, let's say, to these materials. You see, I have here a material defined for the roof roughness. I defined here a sand grain roughness of 2 millimeters with a homogeneous distribution. And this roughness I assigned to the zones of the roof. I say, okay, please use roughness of material 1. And the same here for the roof side 2, but for the columns not. So you have a control to distribute different roughnesses in your model, which have effects of the wind flow around model for your calculation. So even such a task you can solve with these zones and materials. And now, if you have to investigate your model and have to decide the values, if they are interesting, or if you have to use a finer mesh or whatever, sometimes it could appear that you need some special values on a point. Of course, you can use your pointer and can draw it over the structure and you get the values, but sometimes it's interesting to have always the values on the same side. So something like this bubble here. Yeah, and I defined here 2 point probes below the named center of wings, where I said, okay, these are my 2 points, and I can create here tables maybe with the pressure upside and pressure bottom and CP values. All this data is summed up in this table, and graphically in these values, what shows me the bottom value and the top value. No? But, and of course you can create more of them. Yeah? You can say, let's create a new probe and set it graphically. Yeah? Maybe here and here, or on a specific place, and you say with a cut plane, that you say maybe use a cut plane here with on 1 meter, and you want to get here values on a specific line. It's also possible, and you get these values here as point probes documented, and you have all these values here again with values for the specific time step. This is interesting for steady flow analysis. If you have a transient flow analysis, then these values can change over time, and this cries for a diagram. So here use this button for diagrams, and you can open it. I call it diagram machine. Yeah? You have always here on x-axis maybe the time layer from 0 to 11 seconds. You can say here what you want to visualize. On one time, of course, the drag forces, maybe the full resultant, or only an X component, Y component, or Z component. And you can say for what? For maybe whole model, for wing 1, wing 2, for columns. You can select what you want for which quantity. This is only for drag forces, but also for these point probes, what we just defined. Maybe for this point probe 1 on front for center of wings, and the same for front center of wings on the back side. So you can visualize, or you can create your own diagram by selecting all these point probes over time. It's possible. Yeah, and then you have an idea how these values are changing over time for which quantity you select, for example, for this CP value or for pressure. And of course you can export all this data into Excel. Yeah. So this is maybe for nodal values. If you say, this idea with having values on one line is not bad, of course we created here also paths. or we call it line probes. In this case, I defined a center line probe according to this path, which gives you a diagram over the length of the path for this selected time step for the top and bottom layer of the surface, pressure or the p-value. Then you can see here you have positive and negative pressure, how it's changing. If you are interested over time for 0 to 11 seconds, you can also activate here all time layers, what means you get a spectra from which to which values it's changing. Quite interesting what maybe the time effect is bringing. And here you can investigate it. So suction effect have a bigger spectrum than maybe pressure. So if you want to create your own paths, it's also possible. So create here new line probes should be created here with this function here, graph along line probe. And you can use this maybe cutting planes. You can draw it where you need it and draw your path and finish. Then you get it. So this is maybe the investigation on a line. And now we come to one of the last features of our RWIND, maybe this point clouds. For what we need point clouds. Here I want to offer it or explain it with streamlines. So if you check the wind flow around the model, you have here streamline settings and you can say, maybe please check me according such a rectangle, and maybe apply this and show me wind flow for this following points, or for this segment apply, you can change it like you need it, and can follow all these points. But sometimes it happens that you say, I need maybe streamlines for a segment, for a rectangle, and maybe on one side apply, and now you say, what happens on the other side? Could also appear. And for this we introduced point clouds, for example. Here you can make a new point cloud and say, okay, this is, for example, here for the one side. Okay. And then you make a new point cloud graphically, which we move to the another side. Zack, on this side here. Okay. And now you can give the streamline settings the job to show it on point clouds 1, 2, and you get it on both sides. Possible, no? So it's open to you what you create. You can create every step from this multi-dimensional result from our RWIND, and can create for your user quite nice pictures or animations to show how this is acting in the wind flow. And now to my last point, what I want to show you today. So if you have to deal with all this data and you want to document it and to process it somewhere else, I got in the past always the question, can I store it in a table or a text file or whatever? And let's say I always said, okay, you can use the data behind because we store it in a paraview format. This paraview format is an open source format and fits quite well for these numerical results. Meanwhile, we offered this also in our RFEM, so you can also export here paraview files into also all results in paraview format. But in our RWIND, you have here such an export in paraview format, and then you can use it by yourself. To give you a first view, what is this? Let's open paraview. It's, like mentioned, an open source program what you can download. And this is, let's say, visualization environment. and you can load in your data. So open, go to this folder, version 3, okay. And now if you make it visible, you get the rectangle gray block. No, it's 3D data, and you see, oh, here is our Terra formation. So it's only a question how you visualize the data. And you can say now for which time step. You can say, do you want which result, for example, pressure, and in which type, for example, in points, in outlines, feature edges, whatever. And you see even the result is visualized with a colored panel. So all this data is now inside this file format, correctly sorted for further investigations. And you can use it by yourself how you need it. And if you need a table, open a new scheme and go to spreadsheet view and say for this data, and you get a table and you can sort it like you need. And you see there are more options. I think if you feel familiar with this environment, you can create all views and plots what you need. And this brings me to the end of my webinar today, and I give back to Andreas.
Okay, thank you, Andreas, for this nice presentation. I think, all of the attendees could see that that our wind is a powerful tool to calculate wind loads for irregular structures. For what is difficult to find wind loads in the standards. Just try it with our trial version. I can show you how to find our trial version. Just a moment. On our website dlubal.com you can find the free trial versions of RFEM, RStab, RWIND, etc. RWIND is also compatible with RStab 9, but we showed it in RFEM 6 with all surfaces and so on. Okay, in the next days you will get an email to the recording, and you can also find the used model of this webinar. I will show you the website under dlubal.com, and news and events. You find the webinars here. Now, I would like to invite you to the next webinars: data exchange between Rhino Grasshopper and RFEM 6, stability analysis, geotechnical analysis, and so on. That's today's webinar, and as I said, you will get a link to that page. You will find the recording here, and you can already find the model. The model is here that Andreas showed. Okay, and then you can try it with the trial version, or you can release that version as in a trial period. If you have already RFEM 6, just contact our sales team. Okay, then I have to say thank you for your attention. Thanks to Andreas Niemeyer for this nice presentation. Thanks to Markus Baumgartel for answering the questions. I wish all a nice rest of the day. And bye-bye.